All right, I'm going to try to make this fairly brief. So we collected data last week, and then you were supposed to make a paper pencil graph, and then you were supposed to put that data into graphical analysis, which is an app that we started using. I don't know, September, October. I'm not sure, probably September, and haven't used it much since. So I'm going to go through kind of what we had done today in abbreviated version, and hopefully you'll be able to write some things down, and yeah, it'll make sense, maybe, I hope. So what we found out and what we did last time, we wrote down a bunch of equations. Oh my gosh, this is kind of a mess. So this screen here, all these equations, the orange ones are and again, this is first period stuff. So, I mean, obviously the things in your class period, they're going to be different. And last time, actually, we had just started to get these things written down. We didn't even get them all written down in most of the classes. So the orange ones are the ones from your paper pencil graph. And then the blue ones here are from the graphical analysis app. And again, that one looks like this. Let's see, graphical analysis looks like this, where you can get in here. Ooh, oh boy. And you can click on this little deal here and column options, and that lets you rename the column. And again, so on the x-axis, we had time measured in seconds. And so you can make those changes, hit apply, and then you can put your data in. Of course, the y-axis then, column options, we made that position measured in centimeters. And so then you can put your data in, your graph gets set up appropriately then. Also, when you do this, you need to go down here to the graph tools, bottom left corner, click on that. You need to edit graph options, which I don't know if I put this in the last video or not. And you need to click on the always show 0. It's probably going to be set to automatic. You need it to be always show 0. And what that does, on both axes, both of these, always show 0. And what that does is it allows us to have the origin actually be at the corner of the graph, which makes the y-intercept on the graph look like what it really is. And in this case, again, it's over 10. It's over halfway up to 20 here from 0. If you allow the graph to automatically scale it, they will truncate the graph and it will not look like it's supposed to. So I'm telling you, for every graph we ever do, you're going to have to go down here to the graph tools, edit graph options, and change those to always show the 0. We need to see where the origin is, okay? We do not truncate graphs because it makes them look differently than they should. And then once you do that, then you can click on the apply curve fit. And again, it thinks that this is linear. And so that's what I already did here. And so I said, okay, put a linear line on this thing. And it gave me some information here, which again is the M and the B. M and the B are the what? The slope and the y-intercept. So they give that to you. And that's what we did with these blue equations. These blue equations are from graphical analysis. And I want you to notice something here. 40 was what they got on paper, 38-ish. That's pretty close. And a negative 23 here and a negative 16 here. Again, that's a little off, but you'll see some of the other ones here are even closer. 26.7 and 26.52, 11.12 and 12. I mean, those are close. Okay, so that's a good thing. We want your graphical analysis graph with the slope and the y-intercept and the equations that you write out. We want them to be very similar to what your paper pencil stuff was. If they aren't, then that's an indication that we need maybe a little more practice or work with the paper pencil part. So think about that. So that's what you need to make sure is done. You need to make sure your paper pencil graph is done with your data. Your graphical analysis app was pulled up and you graphed that. You got your data in there. And write the equation, the new equation of that line. Let's see. Then Then we started talking about what does this slope mean? Okay. And remember, when we are trying to figure out the meaning of the slope, we pretty much write out a sentence. And the sentence that we wrote out looked like this. There are 40 centimeters of position change for every 1 second of time. Remember, it's the rise over the run. It's the rise over the run. The rise is a position, okay? It's a changing position. And then the run is a length of time. And so we see here that we're looking at around 40 centimeters. And again, I think we kind of looked at group 6 from that class period and said, hey, that's about 40. So there are about 40 centimeters of position change for every 1 second that goes by. And so then we're talking about, what does that even mean? Well, that's telling us what the buggy is. It's telling us how much the position changes every second, so that at 1 second, where would this tumble buggy be? 40 centimeters down the track. At 2 seconds, where would this tumble buggy be? Another 40, right? So total of 80. After 3 seconds, where would this buggy be? Another 40. So now we're at 120 centimeters, and so on and so forth. That's telling us how fast the buggy is. Yeah? It's telling us how much the position changes for every second. That's how fast. So it's a 40 to 1-ish ratio, right? Which means that our position is directly proportional to the time. The position of the buggy, this is the relationship. So what is the relationship between position and time for a tumble buggy? The relationship is that the position is directly proportional to time. That you should write down. Okay? That's the relationship between the position and time. Directly proportional. It is a constant ratio. And that's what the slopes are. And we even found out that group 3, poor group 3, their buggy was terribly slow, 19.33 centimeters for every second, as compared to like 40, 43, 32. There it was a 26, not great, a 38. So again, all these other buggies had way more position change in 1 second than poor number 3. Poor, slow number 3. Didn't even get 20 centimeters changed in their position in 1 second. So sad. So we figured that out, okay? And then we said this. I said, hey, when you found the slope on that line, you took a rise over a run. And the rise is a change in the position. And the run is called a change in time. And so we wrote that out. I said, hey, that's called velocity. In physics, we have a name for that. Change in position over the change in time is called velocity. That's what it's called. Then I said we should have symbols for this instead of names and writing phrases out all the time, because that's just too much. And so I said, hey, do you all know what the symbol is for change in science that we use? It's the Greek letter delta. Delta is a Greek letter, and that is a symbol we use for change. The symbol for position that we use is actually X, which makes perfect sense because you see there's an X in the word position. I know there's not. I was kidding. So delta X is how this reads. Delta X, which means the change in position. I just call it delta X. I know this is confusing because X is the symbol for position, but it's on the y-axis. That doesn't even make sense. But that's the way it is, okay? And then change in time is just delta t. And you literally say it like that, delta x over delta t, which means change in position over change in time, which is, by definition, what velocity, average velocity is. And this is the equation. This is how we write it out, okay? Average velocity is delta x over delta t. Okay, so now we know what the slope means. The slope's telling us the velocity of the buggy, how much its position changes every second. Now, we had to figure out what the y-intercept means, and that was a little confusing. Bottom line, you wrote down a phrase that was supposed to help us figure this out. And the phrase was, hopefully you can look back in your comp book and see it. The value, again, the y-intercept is the value of the y variable when the x variable is 0. So it's the value of the position when the time is 0. When is the time 0? The time is 0 when the clock, what? The last time you will see zeros on that clock is when the clock is started. Okay? When the clock starts, that's time 0. So if we're saying, like for group 2 here, if the tumble buggy was at position 11 centimeters when the clock started, what does that mean? Where was your buggy when the clock started? So I went through and I asked all the groups, and here's what they told me. Some of them said, let's see if I can move this around. There's my buggy. Some of them had a line on the track, and then they measured all their positions from that line. And that line was at the front of the buggy. And so they said, okay, that was our position 0. 0 position, right there at that line. And they measured all their positions from that line. And then the person with the car and then the person with the clock, they were talking and, ready, set, go. And then the car was released and the clock was started. But the graph is telling us that when the clock was started, the position was actually 11 centimeters, which means what? That means, hopefully you're thinking about this, that means that when the person hit the timer, the car had already been moving. So the car was like, once it got to about 11 centimeters, boom, then the clock started. So it was already down the track before the clock even went. Now, was it supposed to do that? Hopefully you're thinking no. So that means there's error here, okay? There was an error between the timer and the releaser of the vehicle. They weren't synchronized. They did not let those two things or have those two things happen at the same time, at the same moment. And so therefore, the data is telling us that the car wasn't where you thought it was when the timer went or when the timer started. Oh, does that make sense? Now, how about all these people? That's the only group that had a positive y-intercept. Everybody else, negative, 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 negative. Everybody else's is negative. Can you have a negative position? Well, if we look at our track here, let's think about this. If that's position 0 and this is position 20 centimeters, what's back here? Negative 20? If it's on the other side of 0, how else would you describe it? Is it 20 centimeters away from 0? Yes. Is this 20 centimeters away from 0? Yes. Well, how can you tell them apart? Can you be in two different places and be 20 centimeters away from 0 position? Yes. And so how do we differentiate? Well, it's like a number line. The ones on the right side, I suppose we'd call them positive, and the ones on the left side, I suppose we'd call those negative, because that's how positive and negative numbers work on a number line. So maybe position can be the same way. We have to have some way to differentiate between whether you're on the positive side of 0 or you're on the negative side of 0. I hope that makes sense. So then why do these people all have negative y-intercepts? Well, it's kind of complicated, but here's what's happening. And on this graph here, on this line, notice I'll try to explain it. Someone suggested that it was because the timer started first and the car hadn't started yet, which means, again, you would have an x-intercept here. In other words, where was the car when the clock started? At position 0, right here at the origin. And where was it sometime later? Still at the origin. Where was it sometime later? Still at the 0 position at the origin, we would say. But it's moving on down the time axis. The time's getting bigger, but the position isn't changing. It's just staying at the same place. Then all of a sudden, boom, the car gets released. Okay, now it can start moving. Now the position starts changing as time goes on. But for that first little section, it didn't go anywhere. The position stayed the same while the time kept going. But we don't have that information. When you draw a best fit, you don't stop at the t-axis and then take it over to the position axis. You keep on drawing the line straight on down to the y-axis. That's negative now, you see. That is a negative y-intercept. It goes down below the 0. So here's what the graph thinks, okay? Here's what the graph thinks. The graph thinks that the buggy started when the clock started, and the only way for that to happen, the only way for the buggy to get to the 0 position and still be at 0 position when the time has already been going is, in the graph's mind, is if the buggy started back here. It thinks that the buggy and the timer both started at the same moment. And the only way for that to have happened, to produce this line right here, is if it was never stuck at 0 the whole time. It actually started behind the 0, and then by the time it got to the clock, or by the time it got to where it started moving, when the time had already elapsed, who knows how much, half second, maybe more, then boom, then we see, okay, now the line is above the position, above the time axis, and it's in the positive. I don't know if this is making any sense, but that never happened. You all did not start your vehicle off of the track. I know that you didn't. I was watching everyone collect data, and nobody started their buggy off the track. But some of these graphs are saying that you did because somebody started the clock and the car just sat there for a little bit, and then it started going. And that shows up as a negative y-intercept. Instead of having a flat line on the t-axis, it shows up as a negative y-intercept. It's telling you your buggy was somewhere that it never was, because it assumes your buggy was moving the whole time. I hope I didn't lose you. And this video is getting too long at this point. So anyway, we found out that the y-intercept should have been 0, but it wasn't, because we didn't start the clock and start the car at the same moment. If we had, then our y-intercept would have been 0. And again, group 6 here, that's pretty close. A couple centimeters, that's like an inch. That's not very much. Okay? And again, even 16 centimeters or 11 centimeters, that's still less than a half a second went by. If these buggies can go 38 centimeters in a second, then only 16 centimeters, that's less than a half a second. And if this one goes 26 centimeters every second, then 11, again, was less than a half a second went by. So these folks, if that buggy goes 40 centimeters every second, then only 3 centimeters, that's a tiny fraction of a second, less than a tenth of a second went by between the clock starting and the car starting. I hope that's making sense to you. So anyway, what you need to do, and this is the assignment that's being posted, okay? Now that we're done with all the data collection, the graphs that you've made, now that we're done with those, I need to see what you did, okay? And so, oh no, this thing is, oh no, why won't this, I can't get the dang thing up. Oh no, Maybe I need to do this. There we go. Okay. Uh-oh. Where did I go? I disappeared. There I am. Okay. So I need to see a picture of your paper pencil graph that has the equation from the paper, from your paper pencil graph, and the equation from graphical analysis from the app. Okay. 2 equations. So the one from the paper pencil graph and the one from graphical analysis. And then I need to see a screenshot of your graphical analysis graph. So this graph right here, a screenshot of this. I need to see a screenshot of your data. So I don't know how that works on the Chromebook. I know on the MacBook, I do Shift Command 4, and that allows me to select a screenshot. So I'm not sure what the commands are on the Chromebook to get a screenshot, but you need to capture this screen with the best fit line on it, with the box here and your data. I need to see that, a picture of that, uploaded with this assignment. Okay. So those are the 4 things I need. I need your paper pencil graph with 2 equations, both equations, and then a screenshot of your graphical analysis graph. So get all that turned in by the next time we meet, and then we'll move on with what's next. So sorry this turned out to be so long. Hope you have a great day. Stay safe out there. Bye.